Hello, my name is Andreas Pusch and I currently work in the group of NATIC in Storks in the School of Photovoltaic and Renewable Energy Engineering at UNSW Sydney. I would like to thank the organizers for inviting me to speak in this conference, and I'm going to talk about how to classify advanced concepts for high-efficiency solar cells. Before we delve into advanced concept solar cells, let us first review a single-junction solar cell. A single-junction solar cell uses the thermodynamic non-equilibrium between the Sun at around 6000 Kelvin and the Earth at around 300 Kelvin into quasi-Fermi level separation between valence and conduction band in a p-n junction. That is, it converts thermal energy into free energy of electrons and holes that can be used to generate electrical power. By converting thermal energy into free energy, the single-junction cell accepts a few loss mechanisms compared to the maximal thermodynamic efficiency. At one sun illumination, so for unconcentrated sunlight, the maximal thermodynamic efficiency is around 74%, as shown by the dashed line here. This chart shows the amount of energy that is lost to different processes that occur in an ideal single-junction solar cell as a function of bandgap of the absorber material. So the easiest one to understand is the below bandgap loss. A photon that is not absorbed by the semiconductor cannot generate power. Now the thermalization loss, if a photon has much more energy than the bandgap, the kinetic energy of the carriers is not going to be used in the single junction solar cell either. So that is also a loss mechanism. Now the below bandgap loss obviously increases with increasing bandgap, whereas the thermalization loss decreases with increasing bandgap. And then there's also the Carnot and the Boltzmann loss, and they are related to the deficiency between the quasi-Fermi level separation and the bandgap. And I'm going to discuss that in some detail later because it's very important in understanding some of the advanced concepts. The balance between these losses gives the optimal bandgap and efficiency of the SQ limit. This limit can be overcome in various ways, and in this talk I'm going to classify the different approaches according to the processes that occur and according to the key assumptions here that are broken. So most of the advanced concepts break the assumption that there's only one absorption threshold in the device and therefore only one quasi-Fermi level separation. Some also break the assumption that each photon generates maximally one electron-hole pair, so that the EQ is smaller than 1. And there's one that breaks the assumption that the carrier temperature equals the lattice temperature. To understand the first key assumption, we need to understand quasi-Fermi level separations in a solar cell. If we look at open circuit, we have the condition that generation of carriers equals recombination of carriers. The difference between the quasi-Fermi level separation of free energy of the carriers at open circuit and the bandgap of the absorber can be expressed to the quantity W or C. The main contribution of W or C stems from the difference between the angle of incoming sunlight, also called the étendue of the illuminated modes, and the angle or étendue of the modes of emission from the cell. This is what was termed Boltzmann loss in the previous diagram. This mismatch in étendue can in principle be reduced by concentrating optics. The contribution from the external luminescence efficiency can in principle be avoided too, and for example for some 3.5 solar cells that are radiatively efficient, like gallium arsenide, this contribution can be very small. The Carnot loss, on the other hand, is unavoidable. Let us now talk about the advanced concepts. We start with a concept that has been successfully realized. It is used, for example, to generate power in spacecraft, and is also envisaged to soon be used in large-scale terrestrial applications. It's simply arranging two or more solar cell materials with different bandgaps in a series connection that is mediated by a tunnel junction. So we now have two transitions, one high-energy transition and a low-energy transition, and the voltage of the device is the sum of the voltages of the individual transitions. If we match the currents, we can get half the current compared to the low bandgap cell, but with more than twice the voltage, so that we get a higher efficiency overall. This concept tackles simultaneously the thermalization and the below bandgap loss because it now breaks the trade-off between the two. Multi-junction solar cells, because they belong into the series connected category of solar cells, require current matching between the different transitions. Now, the spectral content of sunlight varies, so this won't work all the time. And the material combinations available might also not be ideal to current match. Now, if the top junction is luminescently efficient, so that non-radiative recombination is very small in there, then the luminescence from the top junction to the bottom junction can redistribute some of the current and restore current matching. Here you can see how efficient luminescence between top and bottom junction increases its robustness towards non-ideal bandgap combinations. This is calculated for a refractive index of the junctions of 3.6, so the optical density of states in the bottom junction is 13 times higher than the optical density of states in air, so most of the luminescence from the top junction will go towards the bottom junction. If we decrease the refractive index, more of the light will be emitted to the top, and this will not work as well. Now, while the maximum efficiency of this is not quite as high as if you had an ideal selective mirror between top and bottom junction, which is a very theoretical concept anyway, the high efficiency zone extends much further if the luminescence in the top junction is efficient. Multi-junction is the one concept that has surpassed Schottky-Queisser, but what about some other concepts that have not managed yet? There are a number of concepts that have a set of transitions that occur in parallel. So let's call them parallel solar cells. One well-known example is the IBSC, the intermediate band solar cell. Here we have a set of states in the bandgap of the material that acts as stepping stones for a sequential absorption process. Sequential absorption means that it also belongs in the series category and is subject to current matching. These below bandgap transitions occur in parallel to the above bandgap transition, and current is collected between valence and conduction band. What allows these devices to surpass the Schottky-Queisser efficiency limit is that there's not only one quasi-Fermi level separation in the device, but several. Up and down conversion are in essence very similar to the IBSC. The difference is that the current from one of the transitions is now not harvested directly, but rather transferred by luminescence to a conventional solar cell. Luminescent solar concentrators exist in the space of luminescence only. They do not break the Schottky-Queisser limit, so I won't discuss them further in this talk. Just as the series-connected concepts require current matching for optimal performance, the parallel-connected devices require voltage matching for optimal performance. Voltage matching here really means matching quasi-Fermi level separations. So if we have two transitions that occur in series, both of them will encounter the WOC loss in free energy compared to the bandgap energy. If we couple another transition in parallel to this with a bandgap energy equal to the sum of the two smaller gaps, this transition will now have a quasi-Fermi level separation that is more than the quasi-Fermi level separations between the two transitions that we set in series. That is because the free energy penalty WOC, approximately 270 millielectron volt, of the carriers, that is due mainly to the Eton-Due mismatch, occurs twice in the two low energy transitions and only once in the high energy transition. This is the situation you encounter in a conventional intermediate band solar cell. So the intermediate band solar cell has a lower voltage than an equivalent single junction solar cell with the same bandgap. One consequence of this is that the introduction of an intermediate band reduces the efficiency of the intermediate band solar cell unless the intermediate band transitions are very absorptive. This is shown in the graph here, where the efficiency is plotted against the absorptivity of the transitions involving the intermediate band. Intermediate band solar cells are usually attempted with quantum dots, so it is very hard to get very absorptive transitions, especially from the excited states in the quantum dot into the continuum. So how can we match the voltages so that this efficiency drop-off does not occur? To achieve this, we need to make sure that the transitions needed for the intermediate band require combined photon energy that is higher than the bandgap of the main material. In that case, the quasi-Fermi level separations can in principle be matched to each other, and one can do this by using a relaxation step between a bright and a dark intermediate state. This could be because the transitions are spin forbidden, or because electrons in the intermediate band and holes in the redshift band are spatially separated, or separated in momentum space, so that no direct transitions can occur. If we now look at the efficiency of this photon redshift intermediate band solar cell, we see that even a small absorptivity in those intermediate states can increase the efficiency of the device, because the increase in current is not accompanied by a reduction in voltage. And the redshift step still conveys a small advantage in the system with unity absorptivity. So sacrificing a bit of photon energy, around 270 millielectron volt, is definitely worth it to match the voltages. The same principle also applies to optical upconversion. In fact, all efficient upconverting materials have an intermediate dark state. We can also have a second transition that is mediated by Coulomb interaction between electronic excitations. I call those therefore Coulomb mediated. The interaction could, for example, be of Auger type in semiconductors, but generally any interaction that transfers energy from two excitations onto one excitation or vice versa. The Coulomb-mediated luminescence concept have the same limiting efficiency as symmetric sequential up and down converters, but they do not require current matching because there are no sequential transitions involved. Finally, carrier multiplication with two absorption thresholds and Auger-assisted solar cells use neither luminescence nor transitions in series, so they are purely parallel. The Auger-assisted solar cell has been realized with the molecular triplet-triplet annihilation system. This system has a relaxation step from optically excited singlet to a long-lived triplet, where the transition to the ground state is spin forbidden. These triplets then interact and generate a high-energy singlet, and these excited singlets can be directly injected into the solar cell material. Often this device is also called intermediate band solar cell, but strictly speaking, it is different to the intermediate band solar cell because there is no sequential absorption and hence no requirement of matching currents between transitions. The carrier multiplication cell with two thresholds can also be realized with molecular systems. The principle of singlet fission is the exact reverse of triplet-triplet annihilation. One singlet creates two triplets, and there is evidence that it is possible to inject those directly into a solar cell. To ensure that the triplets are injected into the cell and not carriers from the cell injected as triplets into the molecules, the triplets have to have a higher free energy than the carriers in the solar cell. For the singlet fission solar cell, even an endothermic reaction is possible. That means that the threshold for singlet fission is not at twice the bandgap energy of the solar cell, as is commonly assumed when calculating the limiting efficiency of carrier multiplication solar cells, but it is rather smaller than that. Again, by around 270 millielectron volt, so the WOC value. Now, multi-exciton generation solar cells with one absorption threshold do not belong into the parallel section of the Venn diagram. They sit totally outside of this Venn diagram. Every device concept in the diagram can be understood well by simply considering quasi-equilibrium. So all the excitations in a band are in equilibrium with the other excitations in the same band, but are not equilibrated with excitations in the other band. We cannot understand MEG in this context because there are no additional bands or separated states. Therefore, building a model for the external quantum efficiency of a multi-exciton generation solar cell, some example results are shown here, as a function of ratio between photon energy and bandgap, requires analyzing the competition between phonon relaxation and impact ionization. Phonon relaxation, impact ionization. This can only be achieved with a non-equilibrium model. If we want to understand how the voltage in the multi-exciton generation cell arises, we may be able to go back to quasi-equilibrium. Let us look at a simple model for the EQE. The band structure, or the energetic states, are approximated by equidistant states in the conduction band, and the valence states are all set at the same energy. That way, all the excess energy of the carriers is given to the electrons, which constitutes the best case scenario for multi-exciton generation. To calculate the quantum yield, we follow the exciton after an excitation event. If the energy is high enough for multi-exciton generation, there is a chance P impact ionization that the high energy exciton will split into two lower energy excitons, so a bi-exciton. The chance of this happening is proportional to the number of final states that the bi-exciton can occupy. Clearly, this rises with the energy of the initial exciton. Alternatively, the exciton loses energy to the lattice via phonon emission. The higher the initial energy, the more chances an exciton will get to undergo impact ionization. This model is recursive, so we calculate the chance for impact ionization at the lowest energy first and then work our way upwards in energy. The EQE had to be calculated from a non-equilibrium model. To calculate a full IV curve, we also need to calculate the recombination properties of the device. We assume that recombination is much slower than both carrier cooling and impact ionization. That means that we can calculate recombination with the assumption of a quasi-equilibrium distribution. And that means that radiative recombination can be described by the generalized Planck law in such a device. Now, the EQE depends only on the ratio between the cooling rate and the impact ionization rate. But the Auger recombination rate, and therefore the operating voltage, depend on the absolute value of those rates. Therefore, in such a device, the voltage may be reduced a lot just due to Auger recombination, depending on the impact ionization rate and electron energy loss rate in the material. This shows that it is important to properly consider the non-equilibrium processes in an MEG solar cell, and we can't just use quasi-equilibrium. There is one advanced concept that I have not yet discussed in this talk, and that is the hot carrier solar cell. That one has much more in common with a heat engine than a conventional photovoltaic device. There are many interesting open questions on the hot carrier solar cell, for example, regarding how to prevent carrier cooling through carrier-phonon interactions. I want to focus here on the heat engine aspect of exploiting a temperature differential between electrons in the contact and electrons in the absorber. Unlike for all the other concepts discussed so far, the voltage in the hot carrier solar cell does not require a quasi-Fermi level separation. If we consider ideal energy selective contacts, meaning they are infinitely narrow in energy and infinitely conductive nonetheless, we can write down the voltage as an analytic function of the temperature, simply by setting the value of the Fermi-Dirac distribution in the contact, the blue curve, equal to the value of the Fermi-Dirac distribution in the absorber, the red curve, at the contact energy. We can get the IV curve by balancing the energy fluxes at each voltage. Each electron flowing through the contact has the same energy, and therefore if there's no current flow, there's also no energy flow. So if we look at the ratio of the work to the electronic energy flow, we see that this ideal energy selective contact would enable the device to act as a Carnot engine between the hot carriers in the absorber and the cold carriers in the contact. Obviously, the ideal energy selective contact is a purely theoretical concept. Let us consider instead something that can be made, which is a thermionic barrier. So all the electrons can flow above that energy. Here, we do not have a simple analytical function that tells us the voltage for a given temperature. Instead, we have to solve the energy balance at each voltage to obtain the temperature, and from that we get the current as well. The current is now given by the difference between forwards and backwards currents. We have a reduced efficiency of this heat engine compared to the ideal energy selective contact because we get additional heat flow. The carriers emitted over the barrier have a wide energy distribution, and the energy per carrier is larger than the height of the contact barrier. Now we do have heat flow even when there is no net current, and we do not get a Carnot engine. With this overview over the complete zoo of concepts, I would like to conclude my talk. Thank you for your attention. If you have questions about my presentation, feel free to reach out to me.